It's been a long day. So is it already live? So, okay.
I see what you mean now, yeah, because I split it up into 4 parts and I put some of the same choices negative because they're on to the left of the y-axis, and when you add them up, they cancel out.
Yep.
There is no GX.
Yeah. All right. How's everyone doing? Not good. Not good? I'm sorry. So you guys good? Other than him, he's not good. Everyone else okay? It's cold, I know. It's cold, maybe that'll help you stay awake, otherwise you might fall asleep. Don't get too comfy with like blankets and everything. So we're gonna go ahead and get started. How many of you have taken a look at my practice tests and have tried some of them? I know, okay, a few of you. So how many of you do not have Dr. Alexicus? And you've never seen me before in your life? Okay, a few of you. So just to let you know the topics that I'm gonna go over, I have a trust problem on here, so I'm gonna go over some zero force member rules with that. There's a shear moment diagram one. Dr. Alexicus does teach friction, so I'm going to go over friction problems. And then there's centroids and moment of inertia. And as far as those go, I have a composite and an integral one for both of them. So it's pretty comprehensive, I feel like. And then if we don't get through everything, the solutions will be posted on my, my WordPress site. So if you guys don't have it, or if you don't know where to find this practice test, if you want to take a picture of the screen, that is the site where everything will be posted afterwards. Are there any questions before we get started? No, I did not. So also, if you notice, I'm kind of like facing the board as well. So I can't really see you guys if you raise your hand. So if you ever have a question during the review, feel free to just shout it out, like get my attention. I don't want you to like be sitting behind me with your hand up for 10 minutes and I don't turn around and notice. Sound good? So let's go ahead and begin. So for our first one, let's try and get that thing focused a little better. It says, determine the force in members IC and CG of the truss and state if these members are in tension or compression. Also indicate all zero force members. So first thing I always do is I like to highlight which ones I'm looking for. So we need to find IC and CG. So as soon as you see that we need to find two members that are relatively towards the center of the truss, what method would you guys choose? Sections, good. So that's usually a good rule of thumb. When would you want to use method of joints? Yeah, it takes forever, but sometimes they'll ask you to find the force in each member, and then you're going to have to find it anyway. Other times? Yeah, so that's a good point. So if you have, so what is the maximum number of unknowns for method of joints? 2, right? So you only have 2 equations that you can work with. So for method, so for joints, max of 2 unknowns, because we can only do sum of forces in X and sum of forces in Y. What about for method of sections? 3. Give me 1 second. So sections, we have a max of 3 unknowns. I will try my best. Better? Good? Can everyone see it okay? There is a light on here, but it's kind of useless. So let's go ahead and talk about zero force members too. So what are the 2 rules of zero force members? What's rule 1?
2 collinear and 1 non-collinear.
That I call rule 2. So rule 1 I call the 2 non-collinear members. So that looks something like this. And then which of those would be 0? Both are 0. And then what is rule 2? 2 collinear, 1 non-collinear. Does it have to be at a 90-degree angle from the 2 collinear ones? No, it does not. So you can have something like this, and that member is not at 90 degrees, but if you were to do method of joints at this joint right here, so let's do sum of forces in the y direction. There's no outside forces on it, right? So if I say sum of forces in y, that one member is 0. Does everyone see that? So the non-collinear one is equal to 0. So this is for the case where you don't have any external forces at the joint in question. So for this particular problem, let's start listing out our zero force members. So we have, so who sees them? You guys want to just start shouting them out? Go for it.
HI.
So we have HI, which joint?
On H.
So HI, so which rule?
Which rule? Oh, rule number.
So rule 2, so HI, rule 2 at H, okay? So if I come over here, I can say that this one is 0. What else do we have? What was that? BA? So BA as well as BC. And both of those are rule 1 at B. AI, which rule? So if I look at AI, I have a pin right here, so that counts as an external force, so that doesn't work. But good try.
External force.
Okay, so no external forces. Better?
It makes a lot more sense that way.
Okay, fine. Be that way. So we said HI equals 0, BA 0, BC is 0. What else? IG, good. So IG is equal to 0 based off which rule?
Second.
Based off rule 2 at which joint?
I.
Good. So IG is 0.
Wait, really? That works?
Yep. So once we get rid of HI, then we have 2 collinear, 1 non-collinear, that one's 0. So it works. That's why I always put an X through the ones once I.
After you've deleted some of those.
Mhm. Exactly. And then next we can say that CD and DE are both 0 due to rule 1 at D. So that's 0, that's 0. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's all the zero force members that I had found.
Would E make an external force?
What was that?
Is E a ruler?
E is a ruler, but if I'm looking at joint D, so if I look at this joint here, there's no external force. Oh, now I'm not showing that one. If I look at this joint right there, there's no external forces at that joint, therefore the rule applies. But if I were to try to look at E, there is an external force there.
Right, so you couldn't do IH because of the
Right,
rules that
so you saw how IH was 0 due to rule 2 at H. I can't say that JF is 0 at joint F because I have an external force there. Do you guys see the difference? So now what we can do is we can go ahead and jump into the problem and finding our 2 unknowns. So what do I have to do now that I've looked at zero force members?
Find your graph.
Before that.
AY, AX.
Yeah, so let's go ahead. So I always say that zero force members is my first rule. I want to simplify this thing. After we do that, step 2 is our reactions. So what kind of reactions do I have at the pin at A?
AY.
Good. So we have AX, and we have AY, and what do I have at the roller at E? EY, good. So if I do the sum of forces in X, what do I discover?
AX equals 0.
Good. So sum of forces in X equal AX is equal to 0. So now what equation do I want to use to find something? Good, so we could do a sum of forces and y, but we would still have two unknowns. So if we do sum of moments at point A equals 0, I'm going to say that that's the positive direction. So we're going to have 6 times 3, and that's negative. Then we have 6 times 4.5, which is also negative. Then I have EY times 6, which is positive. So I have 6 EY equals 0. So from this, I get EY is equal to 7.5 kilonewtons. Now that I have that, I can do sum of forces in y. So I have AY minus 6 plus 7.5 equal to 0. AY is 4.5 kilonewtons. All right, so we found our reactions. Now what should we do? Good. So ideally, we want to cut through our two unknowns. That's the quickest way to find them. Or is there another way? So we could do method of joints. So we found that that's 0 and that's 0. So that leaves us with 1, 2, 3, but those are all unknowns, right? So we can't do that. Can I cut through this? You see that? How many unknowns would that be? Yeah, so if I cut through here, that's 1, 2, 3, 4 unknowns. Doesn't help me to go the other way, right? So what I would do for this one is I would combine methods. So you can do method of sections and method of joints in the same problem. So what I recommend is making this cut here. Let's call that cut AA. And I'm going to use the left-hand side of this cut because it's easier. So redrawing that. So step 3, method of sections. There's joint I, there's A, that's H. So I'm going to assume that everything's in tension. So is tension entering or leaving a joint? Leaving, good. So I can say that IC is going that way, and this is HG. So IC is the unknown that I'm interested in. So I also have to include, so here's one big common issue that I always notice. Whenever you redraw your cut, people always forget the external forces that are acting on it. So don't forget the reaction force at A. So this is 4.5 kilonewtons. And then for our distances, we know that this is 2 meters, and then this distance is 1.5 meters. So if that's 1.5 and that's 2, what kind of triangle do I have for this vector or for that arrow? 3, 4, 5, good. So this is 3, 4, 5. So we're going to need that in order to break that into components. Everyone good so far? Yeah? So now we can use our EOE. So if I do, so for this one, we're only interested in IC, right? We don't really care about HG. So I'm just going to do sum of forces in Y and find IC. So sum of forces in Y equals 0. I have 4.5 plus 4 over 5 times IC equals 0. So IC is negative 5.625 kilonewtons. What does that negative sign mean? Good. And so which direction is this in? It's in compression. So IC is 5.625 kilonewtons in compression. So we found one. So now what I recommend is we did method of sections. Now let's go back and do method of joints at joint C. So drawing this, I have, scoot it up a little, I don't have much space up here. Give me 1 second. Okay, got it. My papers are all going to fall off the back of this. So we said that IC was in compression. So is it entering joint C or is it leaving joint C? Are you sure? Because up here we have it drawn this way.
It's leaving it.
Good. So if we drew it going away from joint C, that would be tension. We don't want tension. We said that it's in compression. So it's actually entering that joint. So that's 5.625.
I have a question.
Go for it.
So you have I going towards C in the original section, right?
Right.
Doesn't that mean you have to change the direction of that arrow in that diagram?
So we would, but we would have it drawn in tension then. And so if you do that, you would have to plug in negative 5.625. So I recommend just knowing the difference between tension and compression and then putting it that way. Also, in case you guys weren't aware, this stream is being recorded on YouTube and the video for it will be posted afterwards. So everything that I'm doing now, you guys will have access to. Also, my solutions will be posted. So for this joint here, so let's assume tension for CG. So that's going down. And then we also have CJ. And so again, these have the same dimensions as before. This is a 3, 4, 5 triangle. That's the same for CJ. So this is 3, 4, 5. So now, this one, I can't get away with not solving for the other one. I have to use 2 equations. So if I do sum of forces in X equals 0, I have 5.625 times 3 over 5. Then I have plus CJ times 3 over 5. Right? Anything else? No? So that equals 0. So from this, so the 3 over 5 and 3 over 5 cancel. So CJ is equal to negative 5.625. So what does that negative sign mean? Good. So that one's actually in compression as well. So we'll keep that in mind. So here's what I recommend. Whenever you're working on the same free body diagram, don't go back and change the direction because that's whenever you start messing up signs. So while for this one we had IC going this way, and then by the next free body diagram we changed it, we did that because we knew it was in compression. But as soon as you start trying to like change directions on the same free body diagram, I feel like it's more prone to mistakes. So I'm going to leave this the way it is. Yeah.
What do we usually do, like make the arrow on the other side and make it cloud?
What do you mean?
Like compression, like if you find like it's a compression instead of tension, and on the free body diagram, like what my coach told me, like just make the arrow and make it on cloud.
That works. I mean, if that's what your professor teaches you, then do it. But I'm just saying from my experience, if I went back and changed my free body diagrams, I tended to either forget to change it or I would accidentally like plug in the negative value as well. But basically what we're saying here is that this CJ should be going that way. And so however you want to denote that, it's really up to you guys. So now we can do sum of forces in Y. So we have 5.625 times 4 over 5. So that's for this one. Then if I look at CJ, so again, if you choose to flip it, you're going to have plus 5.625 times 4 over 5. If you're like me and you prefer to leave your free body diagram alone, then you're going to have negative 4 over 5 times CJ, and you would plug in the negative 5.625, so you end up with a positive either way. And then we have minus CG equals 0. So solving, we get CG is equal to 9 kilonewtons. What does that mean? Is it in tension or compression? Tension, good.
So you're saying it's best to just leave the signs alone and then just use the negative sign as a way of telling
That's,
tension.
yeah, so that's my preferred like,
That makes more sense.
that's what I like to do. So I generally, I wouldn't report my final answers until the very end of the problem. I would just leave everything alone until then. Any questions about this one? You guys ready for a shear moment diagram problem? I love shear moment diagram problems. All right. So, let's see. So, how many methods do you guys know of for solving shear moment diagrams? 3. Integral, sections, and areas. So areas is the quickest and easiest way. I can tell you guys, if you can see this here, I solved this problem in 2 different methods. I solved it with method of areas, and I solved it with method of sections. So these solutions are both going to be posted, that way you can check your preferred method. I'm going to show you guys method of areas since that's the quickest way, and that's the one that people tend to ask for the most. Is everyone okay with that? Okay. So for this one, before we start it, let's see if we can answer these concept questions. So actually, I'm trying to debate if I want to. Let's go ahead and find our support reactions first, and then we'll go back to the concept questions. So step 1 are reactions. So we have a pin at A. So what kind of reactions is that? So we have X and Y. So I have AX and I have AY. And then I have a cable here. And so that cable, yeah, cables are always going to be in tension. So this is also a 3, 4, 5 triangle. So 3, 4, 5. So there's my free body diagram. I got lazy. I didn't feel like redrawing it.
But the pin up top, you don't have to worry about it.
No, so we're just looking at the beam itself.
Yeah, that's what confused me too, the pin's off.
Yeah, so don't worry about the pin. As soon as you start looking at that one, you would have way too many unknowns. So is there anything else I need to do to this thing before I start solving for my reactions? Good. So if I concentrate this distributed load, it's going to be the area. So we have 250 times 2, which is 500. And that's going to be located right in the center. Right? Okay. So now, if I do sum of, so I'm going to straight away start with sum of moments at point A because it gets rid of the most unknowns. So sum of moments at A equals 0. So I have, for the tension in that cable, the X component doesn't contribute because I have no Y distance, no perpendicular distance. So I only care about the Y component of that force. So I have 3 over 5 times T times 4. And according to my convention, that's positive. Then I have the 500 Newton force there times 2, and that's negative. Then I have this 500 Newton force times 1, that's also negative. So T is equal to 625 newtons.
I have a question. Why is that 500 multiplied by 1?
So,
I see right
got it? Okay.
The distance.
Yeah. Next, if I do sum of forces in X equal to 0, I get AX minus 4 over 5 times T, which we said was 625 equals 0. So AX is 500 newtons. Then if I do sum of forces in Y equals 0, I have AY minus 500 minus another 500 plus 3 over 5 times t, which was 625, equals 0. AY is 625 newtons. Any questions so far? Okay, so as you guys can kind of tell from this, so you know that you have normal shear and internal bending moment, right? If we're talking about internal forces. So generally speaking, you don't have any forces in the x direction. In this problem, we do. Therefore, we know we're going to have a normal throughout this beam. So if I look at the first conceptual question, how does the normal force of that cable contribute to the shear? Does it increase it, decrease it, or does it have no effect on it? No effect. Normal is totally different than shear. And then next question, how would removing the 500 Newton force affect the support reactions at A? So if I got rid of that 500 right there, what would that do to it? AX wouldn't necessarily be 0. So would it increase it, decrease it, or have no effect? It would decrease it. So if you remove some of the forces that it's having to support, you put less of a load on it.
It would decrease AY, right?
Yeah,
Yeah.
exactly. So we found our support reactions. Anything else I need to do before I jump into method of areas? I'm going to introduce you guys to Donkey Kong method if you haven't heard of that before. It's method of areas, but it's a lot more fun. It's the same thing, but it's entertaining. So we found our support reactions. Now we can go ahead and draw our beam. So I'm going to redraw this thing. So I have the 500 for AX, but we don't even care about it. This is 625 newtons, 500 newtons, and then I'm just going to draw the Y component for this, which is 375 newtons. So this distance is 2. That distance is 2. And don't forget, let's use blue. We have our distributed load on here. So that was 250 newtons per meter. Good. So let me give myself a little bit more space. So what's the first thing that I need to do for method of areas?
Continuities or discontinuities?
Good. So we need to go ahead and draw our discontinuity lines. So where will I have discontinuities? So at the beginning. So at this point here. And at the end. Good. So it's at the beginning or the end of the beam. It's at the beginning or the end of a distributed load. It's anywhere you have a concentrated force or a moment. Why didn't I include one right here in the middle of this? Good, that's a distributed load. That force doesn't actually exist there. So we have all our discontinuities. So there's my V of x and my M of x. So here's Donkey Kong method. So, or just method of areas in general. So what you do is you look at point span, point span. So we're going to start at point A or at x equals 0, and we're just going to go from that point to the span between 0 and 2. Then we'll look at x equals 2. Then we'll look at span 2 to 4. Then we'll look at 4. Everyone good with that? So it's point span, point span. So we'll start with the shear first. So at x equals 0, so here's where Donkey Kong comes into play. So if you imagine Donkey Kong running along this beam, this thing is not liking me today. So imagine Donkey Kong's running along this beam. Anytime a force happens, he's either going to get pushed up or down, or as some people said, he takes the elevator up or down. If there's a distributed load, then it's like an escalator, or he takes the stairs either up or down. So whatever happens, up here affects what happens to Donkey Kong right here. It's like the old Donkey Kong game. Everyone good so far? So Donkey Kong he starts here at 0. What happens to him whenever he reaches this point? Yeah, he gets pushed up to 625 newtons. Now what happens to him as he runs along this section here? Yeah, he's going to gradually get pushed down. So if this here is a constant, then what should this graph look like? Linear. Good. So if you integrate a constant number, you get a linear equation. So he's going to get pushed down a total of 500. So that means we're going to end up right here at 125. And we said that that is a straight line. So now what happens to Donkey Kong whenever he reaches this point here? Whenever he reaches that point? Yeah, so that 500 Newton force knocks him down. So he gets pushed straight down to negative 375. Now what happens to him as he runs along this part of the beam? Nothing, nothing, nothing. So he just goes straight across. And then what happens whenever he reaches the end point? He gets pushed up 375. So back to 0. And so we're doing good. So if I were to write this out to show proof, so at x equals 0, we can say that v is equal to 625. So he gets pushed up to 625. Then if I look at x is between 0 and 2, we have v is equal to 625 minus 250 times 2, which gives us 125. Next, I look at the point. So at x equals 2. So he goes from 125 down 500. So v is negative 375. Then if I look at x is between 2 and 4, v equals constant. So it's still negative 375. Then when we reach x equals 4, he goes back up to 0. And so that's how you can show proof with it, yeah.
How did you get the 375? Where did that come from? 125, 125.
Yeah, this here came from 125 minus 500.
No, I mean, like, how did you, like, you just went back up to 375?
The support reaction right there.
Yeah.
So you go from negative 375 plus 375 takes you to 0, yeah.
If you didn't go to 0, you had a problem.
I
What?
think you wondered whether
If you
you did
didn't
that
go to
value.
0.
Yeah, where did you get that value from? That's why.
Value.
What value?
The 375. That's what
Oh.
it's from.
So if I, hold on you guys, hold on. So if I come back over here, if I only want the y value, I can say that the y value for the tension is equal to 3 over 5 times 625, which gives me 375. Sorry. We're all good. Because if you were to look at the x value, that one should be 500. Because the normal doesn't change throughout this beam. All right, so now we have to look at our, yeah.
The fact that we have a normal in this question still doesn't affect the shear at all.
No. So normal, so that was actually the first conceptual question on here. Normal has no effect on your shear diagram. So now for our moment, we know that the moment is the integral of shear. Therefore, it's going to be the area under the shear curve, right? So if I look at this endpoint here, so again, we're going to look at point span, point span. So at x equals 0, do I have any sort of concentrated moment? No. So we start at 0. So moment equals 0. Now if I look at x is between 0 and 2, my moment, it's going to start at 0, but then what do I have to add to it? So I have this change. So we have to find the area of that. So if I draw a line here, I have a triangle and a rectangle. So I'm going to have, so this is all positive, right? So I'm going to add. So we have 1/2 times the base, which is 2, times the height, which is 625 minus 125. So that's just 500, right? So that's for the triangle. Then for the rectangle, I have plus 2 times 125. So my moment at x equals 2 should be 750. So we start at 0, and we end up at 750. And then I'm going to go over how we find the shape of that in a second. So next, if I look at x equals 2, do I have any concentrated moment at that point? No. So moment still equals 750. So there's no jump in the graph at all. So now if I look at 2 to 4, so my moment is equal to 750, but what happens to it?
Subtracted the area.
Good. We have to subtract that area. So we have minus our base, which is 2, and the height of that is 375. So our moment, if you find that, is equal to 0. So we're back at 0. And so if that here is a constant, what is the shape of that section going to look like? Linear. So it's going to be a straight line. I missed. That's a straight line. Everyone knows that I'm an artist. Okay, so 375 is the height of this rectangle, right? So I know that at this point here, it's negative 375. So it's 375 times 2 to get the area of that. That's all. So it's the area under the shear curve. So now to find the shape of this part. So I have a little saying, and I know those of you who come to my sessions already know it, but don't steal my thunder. So if I draw this little circle here, this is going to help us. So please don't neglect infants. Neglect dumb people instead. So here's how this works. So what you do is you take and you look at the shape. So this here helps to predict the shape of an integral of something. So for example, it works for going from distributed load to shear. It works for going from shear to moment. So if I have something like that, and that. So here's how this works. I don't have enough space. Okay. So this shape right here, is that positive or negative? If it's above the line. So this is positive. Is it increasing or decreasing? So that's positive, decreasing. This one right here, positive or negative? Increasing or decreasing? It's getting more negative, so it's increasing. This one here, positive, increasing. This one here, negative, decreasing. So how this works is you take and you look at the shape of the circle outside of where it is. So positive, decreasing does that. Negative, increasing does that. Positive, increasing does that. And then negative, decreasing does that. Oh my goodness. You guys get the idea. So you just look at the outside of the circle. So if I come back to our problem here, is this shape right here, so for my shear, is that positive or negative? Is it increasing or decreasing? So that's positive, decreasing. Therefore, our shape looks like that. So for the most part, I always use this method of areas. The only times where I will use integrals or sections are if you have a point where the shear is equal to 0. So what does that mean if you have shear equal to 0? Good, you're going to have a maximum moment. So you have to find what the maximum moment is. So for those of you who are civil, aero, or mechanical, and you have to take solid mechanics or mechanics and materials, you're going to have to do shear moment diagrams, and you're going to have to find where the maximum moment is. So this is, whenever you have to do that, I would recommend using sections or integrals. The other time I recommend it is if you have a triangular distributed load. because those get really complicated. So if I have a triangular distributed load, which is a constant, what do I have for my shear? So if I integrate a constant, or if I integrate a linear, if I integrate a linear, what do I get? Quadratic, right? And then, so my shear would be quadratic. If I integrate that to get my moment, what would I get? Cubic. So I don't know about you, but I have a hard time finding areas under quadratics. So I'd rather just use integrals or sections for that. Are there any questions for this problem? Yeah?
How's the second one negative increasing?
So you look at the magnitude of it. So if I look at a little piece right there, that's a really small negative number. It's almost 0. But then if I look at a piece over here, that's a really big negative number. So essentially it is getting more negative. So it's negative increasing.
As opposed to negative decreasing?
Yeah, so negative decreasing, if I look right here, I have a very large negative number. But if I look at a little piece right here, I have a very small negative number. So it's going from big to small.
Oh, okay.
So that one would be decreasing. All right, you guys ready to move on to some friction problems? How many of you did your professors teach friction? No? I know that the majority don't. So these, if you're going to take dynamics, these will definitely help you. So essentially it goes back to physics and drawing free body diagrams, so it's not too bad. So we're going to go over 2 of those really fast, and then we'll jump into centroids.
I have a question.
Go for it.
Fluids should be in here on the final. I forgot the fluid.
Oh, did your professor teach the fluid pressure stuff?
I don't think so.
If he didn't teach it, I wouldn't worry about it, but it doesn't hurt to know it. So I know that Dr. Alexakis did not teach the fluid pressure stuff, so I didn't put any on my review. All right. So for this problem, it says, this car has a mass of 1.6 megagrams and a center of mass at G. If the coefficient of static friction between the shoulder of the road and the tires is 0.4, determine the greatest slope theta the shoulder can have without causing the car to slip or tip over if the car travels along the shoulder at a constant velocity. I can tell you, I just did a dynamics problem this morning that the first part of the problem was identical to the process in this, to find the theta that would cause something to overcome friction. So this is really important stuff. So what we need to do is draw, well, before that, we can go ahead and write the mass in kilograms. So what is megagrams to kilograms? Good, 10 to the 3. So we have 1.6 times 10 to the 3 kilograms. And just for the sake of having it down, we know that the static coefficient of friction for this is 0.4. So we're going to draw our free body diagram. So I know that at my center at G, so right there, that's where I have the weight of the car. And then, so here, you guys like my car? There's a tire. There's a tire. So on each, don't laugh at my car. It's awesome, okay? So here we have a normal at B. And here we have, oh, that W got in the way. Here we have our normal at A. No, that's the car. Here's the road. Stop it. Don't question it. It's a very low profile car, okay? So now you got me like distracted by my own drawing. So for this problem, it says, find the greatest slope theta the shoulder can have without causing the car to tip or slip over. So if this thing is just about to tip over, what can we say about the normal reaction at B? It's 0. Good. So anytime you have something that's just about to tip, the weight is being supported by one side of it. Okay, so we're going to say that NB is equal to 0. So in that case, our friction is only acting at wheel A. So I have force of friction at A. Let's see. So we know that this height between point G and the road is 2.5 feet. We know that the distance between A and B, or the contact points, is 5 feet. I kind of don't like the way I drew this. Ignore this line there. I'm going to draw the weight up here. It was kind of in the way. Hey, I wrote it in pen too, okay? So get over it.
So this problem, why do they have feet instead of meters? I mean, you have kilograms, feet. Why would you have pounds, feet instead?
You know, that's a really good point, and I just noticed that. But it ends up not mattering because you're trying to find an angle anyway. But that's a really good point. I guess you would have to go back to chapter 1 and remember all your conversions.
Right.
So let's see. This angle right there, there's our theta. So I'm going to use a tilted axis for this. So if I draw a line perpendicular to that, what is this angle here? Good, that's also theta. So I need that to convert W for my tilted axes. So first thing we're going to look at is tipping for this. So I'm going to do sum of moments. So if I do sum of moments about point A equal to 0, I have W times the cosine. So remember, I'm looking at tilted axes, but even then it doesn't matter. So this W, we need to convert it or get it in components like this. So this is what I would do. Do you guys see those okay? Is that a yes? I just heard silence. So this component right here is going to be W, so that's the cosine of theta. And this one is W sine theta. What was that?
What is that? Is that just
I just found the components. Yeah, so I found the X and Y components, and here's the axis system that I'm working with. So I'm going to say that that's my x-axis and that's my y-axis, just to make it easier. So
you lined up with a ramp.
Yeah, so doing it this way, I only have to resolve one of my forces into components, whereas if I do it the other way, I have to resolve potentially 3 of them if I have a normal at B. Yeah. The normal, so if there's no, okay. So you know that force of friction is equal to mu times the normal, right? If the normal is 0 at that point, there is no friction at that point either. Good question. So for sum of moments about right here is my point A. My diagram got a little messy. Sorry. It's been a long day. So we have W times the cosine of theta. So I'm looking at this component. And then I have to multiply that by the perpendicular, which will be 2.5. Does everyone see that? So the distance from here to there is just half of 5 feet. So you could do this problem the other way where you don't tilt your axes, but it's really good to learn it now. And so that is negative. Then I have the W sine theta, and that's going to be times 2.5 feet also. And that one is causing a counterclockwise rotation, so that's positive. And that equals 0. So those just cancel, right? 0 equals 0? No. Cosine, sine. Be very careful. So looking at this, I can cancel that, I can cancel that, but then I'm left with sine of theta is equal to cosine theta. Do you guys know where that is? 45 degrees, good. So if you weren't sure, you can divide by cosine and say that tan theta is equal to 1. So theta inverse, or tan inverse of 1, theta is equal to 45 degrees. So that is the angle it needs to be at for it to tip. So now for slipping. So this is where things get a little interesting. So tipping is a bit more straightforward. Because the normal at B is 0, and if I took the moment at point A, the normal at A has no perpendicular distance, because it's at point A. So I took the moment at that point. So now for slipping. So what we do for this, so I'm going to draw a different free body diagram.
Is this part of the question?
Yes. It says, determine the greatest slope theta the shoulder can have without causing the car to slip or tip.
Okay.
So we have two different things we have to look at. And one wheel is bigger than the other. This is totally a normal sports car. So there's my center G. I have the weight. And then here's this theta. And so for slipping, what we do is we apply just one total frictional force and one normal. I know a lot of you haven't seen this before, so I wouldn't worry too much about it if your professors didn't teach it. So what you do is you say, so again, these are my axes. This component right here is W cosine theta, that component W sine theta. So sum of forces in X, I get F minus W sine theta equals 0. So where did I get that? Oh, so we also know that friction is equal to mu times normal. So that's equal to 0.4 times the normal. So I'm going to plug that in for friction. So I have 0.4 times n minus W sine theta is equal to 0. So then if I do sum of forces in y, I have n minus W cosine theta equal to 0. So n is equal to W cosine theta. I can take that and plug it into the first equation. So I get 0.4 times n minus W cosine. I plugged it into the wrong spot. 0.4 times W cosine theta minus W sine theta is equal to 0. So that and that cancel. So you get 0.4 cosine theta is equal to sine theta divided by cosine. You get tan theta is equal to 0.4. So solving, you get theta is equal to 21.8 degrees. So the maximum angle, so that it doesn't slip down the slope, would be theta is equal to 21.8. Since that is less than 45, the maximum angle, therefore, would be 21.8. So this car would slip before it would tip, which makes sense, right? How many cars do you see just randomly tip over? Whereas I'm sure all of you have felt your tires spin at some point. Fair? So it's more prone to slippage than it is to tipping. Any questions about this? Okay. So the next one we have is another one of these, but it's a little more straightforward. So it says, the coefficient of static friction between the man's shoes and the pole is 0.6. Find the minimum coefficient of static friction required between the belt and the pole at A in order to support the man. He weighs 180 pounds and has a center of gravity at G. So we're going to draw our free body diagram. So there's point C, point A, there's point G. So I know,
No, point A and C have an offset.
you're right, sorry.
Yeah, that threw me off too, but that's my.
Yep. I mean, my line's already slanted somewhat,
That's
but
what I did my normal.
I just noticed that too. So we're going to do this. Point A, going to make it more noticeable. Point C, point G, and then there's the belt that connects those. I just got pin on my shirt. It doesn't matter. Not for this one. So we know that we have a normal force at A, and to keep him from, so keep in mind that friction acts in the opposite direction of motion. So if he's trying to climb up this thing, where is his body actually trying to go? Down. So he's trying not to fall. So therefore, which way does friction work? Up. Good. So I have force of friction at A. Then on this side, I have my normal at C, and then friction at C, and I have his weight at G. And so for distances, we have, let's use a different color. So the distance between A and C is 4 feet in the Y and 0.75 in the X. And then the distance between C and G is 2.5 feet. I put 2. Okay, good enough. So now if we do sum of moments about point A, we get, let's see, so we have force of friction right here. So I can say that FC, the force of friction at C, they tell us that mu S is equal to 0.6. So I can say that this is 0.6 times the normal at C. So solving for this, I have my normal at C times 4. So that's positive. So I have 4 times NC. Then I have the frictional force times 0.75, and that is also positive. So I have plus 0.6 times NC times 0.75. And then I have his weight, which is 180. That causes negative rotation, and that is 3.25 equals 0. So from this, the normal at C equals 131.46 pounds. Sorry. Then if I do sum of forces in X equal to 0, all I have is NC and NA. I can say that NC minus NA is equal to 0. So NC equals NA, so NA is also 131.46 pounds. Now I can do sum of forces in Y. So I can say that FA plus the friction at C, so that was our 0.6 times NC, which was 131.46, and then I have minus 180 equals 0, so I get FA is equal to 101.12 pounds. So that's the frictional force required to keep him up, but we're asked for the coefficient of friction at that point. So we can say that FA is equal to mu S times NA. So mu S that we're looking for is FA over NA, so it's 101.12 divided by 131.46, which gives you 0.769. What should our units be? Good, no units. And that's our frictional coefficient. So the key concepts for friction is, don't forget that it's mu times the normal. And then, let's see. That's pretty much it. Like in friction also, it opposes the direction of motion. So let's move on to some fun stuff. My favorite. So we got like 1 hour left and we are halfway through this thing. So this problem says find the centroid x bar and also y bar. So I always start with writing my equations. So for x bar, what is our equation? If I'm looking at integrals. If I'm looking at integrals, it's the integral, right? So it's the integral of x squiggly or x tilde times dA divided by the integral of dA. And y bar is the same, but with y. Good? So now let's start with x bar. So for x bar, I'm going to redraw this. So if I want x bar, do I want things in terms of dx or in terms of dy? Dx. So we want the little piece like this. So this is dx, and then we have our height. So the height of this is going to be top minus bottom, right? So the height is just equal to our equation for y, which is x squared. So it would be x squared, yeah. Good. So moment of inertia, so yeah, that's where these do get confusing, is that they flip. But the way I remember that is moment of inertia has moment in the name. So whenever you're taking the moment, for example, about the x-axis, you look for y distances, right? So I always, keeping that in mind, I think that they flip, if that makes sense. Whereas for centroids, it's like a weighted average is what we're trying to find. So we're finding the average x location for the figure. Good question. So for this problem, so the hardest part about these is finding what dA is. So for this one, dA is equal to x squared times dx. So I can go ahead and find my total area, right? Because that one doesn't change between x bar and y bar. So I can just find it and use that. So I can say that A is the integral of x squared dx. What are my bounds for this? If this is 1, and this is 2, and that's 1, and that's 4, what do I use? 1 to 2, good. So if we're looking at x's, we want to make sure we use x's. So that's the integral from 1 to 2. So this gives us 1/3 x to the 3 from 1 to 2. So our area is 7/3 inches squared. And so we can use this for both parts of this problem. So now for x bar, we just plug and chug. So we have the integral of x times dA, and we said dA was x squared times dx, divided by the integral of dA, but we already found that. That's just a. So this is divided by 7/3. And what are my bounds for this integral? 1 to 2 again. So this is equal to the integral from 1 to 2 of x cubed dx. And I want to get this thing out of the denominator, so I'm just going to flip it. So I have times 3/7. So this gives me 3/7 times 1/4 x to the 4 from 1 to 2. So you end up getting 3/7 times 15 over 4. So x bar is 1.607 inches. Now, does that value make sense? So 1.6 would put this, yeah, I would put it right along this line right here. Does that value make sense? Yeah, it's reasonable. It's within the figure. And it's closer to the taller side. So now for y bar. So this one gets a little tricky. So now we have to find our differential area again. So we have that. And so if I'm finding y bar, do I want dy or dx? Dy this time. So I need this shape here. So there's dy. What is this height or this base for that? Yeah, that's just a constant of 1. But then what happens once I reach this point? The shape changes. So I have two different figures I have to look at. So that's dy. And then this value here, you said it already. Yeah, so it's actually equal to, so it's going to be, okay. So whenever we're looking at, whenever we did x, we did top minus bottom. For this one, we have to do right minus left. So for right minus left, if this was at 1 and this value here was at 2, then I'm going to have 2 minus the square root of y. Everyone see that? That's because this equation was y equals x squared. Therefore, x is equal to root y. Yeah, you just solve for x. Because you want everything in terms of y for this.
Why did you get the 2? Where did 2 come from?
We had to do right minus left. So if I look here, I did that point minus that, or that curve minus that curve. So it's 2 minus root y. So now we just plug everything in. So y bar is equal to the integral of, so for this first one, so I'm looking at the rectangular or the constant shape. I have y times my differential area, which is just 1 times dy. And that's from 0 to 1, right? So that's 0, that's 1, and way up here is 4. Then I have plus the integral from 1 to 4 of y times the next one, which is 2 minus y to the 1/2 dy. And all of this is over the area, which doesn't change. It's still 7 over 3. So simplifying, we get, so if I integrate y, I get 1/2 y to the 2 from 0 to 1 plus, so that's 2y. So that gives me y to the 2, and then I have y to the 3 over 2. Does everyone see what I'm doing? So if I distribute this y right here, I have 2y, and then I have minus y to the 3 over 2, right? So whenever you multiply them, you add the exponents. So if I integrate that one, I have 2 over 5 times y to the 5 over 2 from 1 to 4. And again, this whole thing is over 7/3. So if you plug all of that in, so I went ahead and just, I'll write it out. So we have 3 over 7, so I took my denominator and I flipped it. So for this one, the first component, or the first term is just 1/2 minus 0. Then for this one, we have 4 squared, so plus 16. Then we have minus 2 over 5 times, 4 to the 5 halves, which is the same as 2 to the 5. Then I have minus 1 plus 2 over 5. So there was an extra negative in there. I went ahead and distributed it. So simplifying, you get y bar is 1.607 33 inches. So coming back up to our diagram, 1.33 would put us approximately right there. So there's our centroid. Does that centroid make sense? Yeah. Yeah. Two minus root y. So we have to do right minus left. So the rightmost point is 2, and then whenever we go left, we hit y equals x squared, but I need that in terms of y. So that's just x equals root y. Yeah. I just said it. So it's right minus left. So 2 minus that equation, which is just root y. You guys ready to move on? You guys look like you hate this problem. I just see it on your faces. So the next one,
Easier this way or does it get?
I like my way. I have this. I went to the or the 11th edition of the textbook to find this problem. I like this problem. So I'm going to show you guys my method. So step 1, we got to write our equations. So for composite centroids, we know that x bar is the sum of our x tilde times a over the sum of a. Then our y bar is the sum of y tilde times a over the sum of a. So I like to make a table for these. It makes things a bit simpler. So step 2, we make our table. And so to figure out what to include in the table, we look back at our equations. So we need our segment, or our figure, whatever you want to call it. We need area, we need y tilde, we need x tilde, then we need y tilde times a, x tilde times a. Are my lines spaced evenly enough for you? It's acceptable.
It doesn't really make a table unless you're touching.
Oh my gosh, so picky. All right, so how many figures do you guys see for this?
4.
What's the minimum number of figures you can come up with for this one? I heard 3. 3 is what I came up with. So I saw this as one big rectangle, and then I subtracted a triangle, and I subtracted a quarter circle. So I'm going to redraw each figure within my table. So for figure 1, I'm going to call that my rectangle. 2, 3, we'll get into that. But before that, for our equations, so we said that we needed the sum of x tilde a and the sum of a. So I always come over here and I say, okay, well, I need a summed up, I need that one summed up, and I need that one summed up. So I like doing this in the table because I feel like I make less mistakes this way. So for segment 1, I just have this lovely rectangle with its centroid right in the middle. So that's 10 inches, and this is 6 inches. Then for figure 2, I'm going to call that make that my triangle. So that's 3, and the height. So what is the height of that triangle?
3.
It's 3, right? So the height of this is equal to the radius of that circle, which is 3. So that's 3, and I should have made that a little bigger, but the centroid for it will be right there. So it's going to be, well, we'll get to that in a second. This height here is also 3. Then for the next one, we have that semicircle, or sorry, the quarter circle. And this is the one that gets really weird, but in the back of the book, there's a table that gives you these R, or the centroid values, and I'll tell you what that is in a minute. So let's just jump into this thing. So area of the rectangle is going to be base times height, 60. Area of the triangle, 1/2 base times height. So good. I'm so proud of you. Oh, it was? I thought it was you.
I got it, yeah.
Like you were looking at me whenever I heard it too, so I was just like, yeah.
So I was waiting for you to be like,
So this is important. So that triangle doesn't actually exist, so it's a negative value. And then same thing for the quarter circle. So for this, we're going to have pi times r squared divided by 4. So it's negative 7.069. So if we add all of those up, or 60 minus that, we get 48.431. I just said it. Like you needed to see it too? Gosh, you're so picky. Okay. So now I need to find my y tilde and my x tilde. All those are the centroids of the individual figures. So for this one, my y tilde is going to be 3, and then my x tilde is going to be 5. Now for the next one. For my x tilde, it's going to be 1/3 of that base, right? So 1/3 of 3 is 1. Then for the y, it's going to be 2/3 of 3. So 2, but then plus 3, right? So that total distance is 5. Everyone okay with that? Yeah. No, we're about to get to that. Why are you jumping ahead of me? You're so eager.
Could you explain that again about the y direction for like?
Right. So if I drew that a little bit bigger, you know the centroid's right here, right? So you know that the center of the triangle would be 1/3 from the tall side or 2/3 from the small side, right? So 2/3 of 3 would give me 2. But then I'm looking at the distance from the x-axis, right? So I have to add 3, right? So that gives me, did I plug these into the right spots? Yeah, I did. So for my y bar, I have 5. My y tilde, I have 5. X tilde, I have 1. Now for the quarter circle, it's in the back of the book, but I had the equation memorized because I've done it so many times. The center is equal to 4r divided by 3 pi. So that is equal to 4 times 3 divided by 3 pi. So that's 4 pi. And that's measured from the interior of it, I guess you could say. So this here is 4 over pi, and then this distance here is 4 over pi. Do you guys see what I mean? So it's measured from the straight part of the quarter circle.
So your x is 10 minus 4 over 5?
Good. So let's start with our y value though. So for our y value, we know the total height of this thing is equal to 6, right? But I want this distance, right? That's my y tilde. But I know that the difference between those two is 4 over pi. So this is equal to 6 minus 4 over pi, which is 4.727. And then it's the same process for the x. So it's going to be 10 minus 4 over pi, which gives me 8.727. Everyone good with that?
why is it minus not plus?
Because we know that I'll draw it a little bigger. So for this quarter circle, so I know that the height from the top of it down to my x-axis is equal to 6. Yeah, but then the value that I know for the centroid is that little piece there, which is 4 over pi. But I'm not interested in either of those. I'm interested in their difference. And it's the same thing for the x tilde. So now all we do is we just start multiplying. So y tilde times a, so 3 times 60 gives me 180. 5 times 60 gives me 300. Then for the next figure, I have 5 times negative 4.5, which is negative 22.5. Then I have 1 times negative 4.5. Then I have 4.727 times negative 7, whatever that is, negative 33.412. And then the same thing for x. I have negative 61.686. So then I add all of those up. For this one I get 124.09. The other one I get 233.814. I saw the 8 in the decimal and then I made them into 8s. So now what I can do is say that my x bar is equal to x tilde divided by a. So that's 233.814 over 48.43. That gives me 4.83 inches. And then y bar, 124.09 over 48.43. So I get 2.56 inches. And now let's just make sure that those make sense. And then I'll show you the answers again. So for y bar, I have 2.56. So that is somewhere along this line here. Then for x bar, I have 4.83. So that is approximately right there. So there's my center. Does that value make sense? Good. Any questions about this? I will.
Question. If you ever got a result that didn't make sense, does that mean that you did the math wrong, or does that just sometimes happen to get wrong?
Generally, that probably means you did the math wrong. So for example, if we found that our centroid of this thing was like over here on this edge, that doesn't really make sense. Or if we found that it was like way up there, this is, so what these, that could make sense depending on the kind of centroid you were looking at, but this is center of area. So we're just finding the average of the area, essentially. So essentially, it should be in the visible center, or what we would assume would be the center. Any other questions about this one? You guys ready for a moment of inertia? No?
Do you think it's faster to just divide up into 3 and subtract the 2 as opposed to 4 like I did? I try and go.
It works either way. For me, I just try to get it in as few figures as possible. All right, last 2. We can do this. So, conceptual questions. True or false? Ix is equal to the integral of y squared dA.
True.
You sure? You sure it's not x squared dA?
I'm sure.
You're certain? Okay, you're right. So this is true. So as I said before, I always remember it's moment. Therefore, moments, I look for perpendicular distances. So if I want Ix, it's y squared dA. If I want Iy, it's x squared dA. So that's how my brain works. Huh?
Draw variables.
Yeah. Don't you love the variable problems? I know. It's okay.
Very frustrating.
So number 2 says Ix must be solved for with dx. False. So just like what we said before, it's flipped. So it has to be dy. When is parallel axis theorem needed?
When the centroid axis doesn't correlate with the
Yeah, so-
global axis.
Good. So whenever the axis that you're trying to find the moment of inertia about is away from the centroid of the figures, right? I don't know how to put that into writing.
I didn't even get what you said.
Don't worry about it. What? So how about this question? How about this question? What is the equation for parallel axis theorem that you guys know of?
Is the Ix equals Ix prime plus,
Y squared, y bar squared.
yeah.
Huh?
Y bar? No, definitely not.
It's not.
She just right what she
No,
said.
it's supposed to be area times.
Okay, there you go. So it's a. So for Ix, it's Ix prime plus a dy squared. Then for Iy, it's Iy prime plus a dx squared. So the only thing with these is that they flip. All right, and then what are the units for moment of inertia? Good. So feet to the 4th. All right, so this problem says find the moment of inertia of the shaded area about the x-axis and then about the y-axis. So in order to make sure we get to the composite moment of inertia one, if you guys are okay with it, let's just do one of them. Do you want to do the x-axis or the y-axis? X, y, yx. So that's the first one. So you're just choosing because whatever. So let's do it about the x-axis then. I will post these solutions, and if we have time at the review, we'll go back to this one. But again, they will be posted. You can check it later. But I want to make sure we get to the composite one. So for x-axis, we know that our equation is Ix is the integral of y squared dA. So we need to find what dA is. So that's always step 1. So if I draw this lovely figure, this top equation is y is equal to h over a times x. And this one is y is equal to h over a squared times x squared. And then this is a, that is h. So if I'm looking for Ix, do I want things in terms of dx or dy? dy, good. And that's based off our equation. So we want, not that one. We want this differential area, right? So we want dy. So for our height here, we need to get both of those in terms of y, right? You guys see it? So for this one, so y equals h over ax, I can say that x is equal to a over h times y. Then for this one, x is equal to square root a squared over h times y. Right? That looks good. And then if we wanted to, we could simplify that and say it's a over h to the 1/2 times y to the 1/2.
Easier with exponents.
Yeah. Okay. So now what we do is we know that dA, so for that length, it's going to be right minus left. So it's going to be a over h to the 1/2 times y to the 1/2 minus a over h times y, and then times dy. Everyone good with that? So we just did right minus left. So it's the same process that we did with the centroids. So now this is just a matter of plugging and chugging. So we get Ix is equal to the integral of y squared times, I'm so lazy, all of that stuff.
I usually write squiggle when I do that. Or just write junk.
This thing. Okay? And then our bounds for it, are they 0 to a or 0 to h? Who says a? Who says h? Are we looking at x or y? We're looking at y. Everything is in terms of y, therefore our bound should be y. So this is 0 to h, not a. So to simplify this, we have the integral from 0 to h. So I have y squared times y to the 1/2. So this gives me a over h to the 1/2 times y to the 5 over 2. Then I have minus a over h y to the 3 times dy. This is lovely.
Do I to 5 over 2?
So I have y to the 2 times y to the 1/2. So that's the same as saying y to the 4 over 2 plus 1 over 2,
Yeah.
which is 5 over 2. So, oh my goodness. So Ix, I have a over h to the 1/2. That's y to the 5 over 2. It's going to be 2 over 7. Y to the 7 over 2 minus a over 4h y to the 4 from 0 to h. See, this one's not too bad, right? It's not the worst thing in the world.
It definitely sucks.
Yeah, it's pretty bad. So Ix is 2a over 7h to the 1/2 times h to the 7/2. So what happens to that?
Gives h of 3.
What was that?
Gives h of 3.
H of 3. Does everyone agree? Okay, good. So that is, I'll write that in the next line. 2 over 7a, and we said that's h to the 3. And then this is minus a over 4h times h to the 4, which becomes h to the 3. So minus a over 4, and that's that loveliness. So 2 over 7 minus, wait. Oh, I started looking at the wrong problem, yeah. So that's 2 over 7 minus 1 over, yeah, it is. I was trying to check my work as I went. Yeah, that's right. So it's a h to the 3 over 28. No. Actually, I can't because it's getting pushed back by the papers. Any questions about this monstrosity? IY is a lot simpler, by the way. IX was the more difficult one, which is why I thought that's why you asked for that one, but yeah, because you don't have all the 1/2 powers and all the craziness.
I know the H and A are flipped, but are the denominators supposed to be different too?
For IY versus IX? I mean,
I don't know your solution, I don't want to take time.
achoo.
Oh, that's what I got, good.
HA to the 3 over
Yeah,
20.
yeah, I thought for whatever reason that it had to be 28 as well.
We'll go over that one if we get time, but this next one is a very good problem. and could very well be on the final.
3D?
It's, okay, it's 3D, but the X component, it's,
Not as big.
yeah, it's the same. Like, it's the same shape all the way across. So it doesn't, you don't need to,
Draw it in 2D?
yes.
Yeah, I redo it in 2D. Yeah.
So here's some conceptual problems that you can answer without calculating anything. What is X bar for this problem? 0, good. Why is it 0?
It's right through the.
It's symmetric about the y-axis, right? And then what is Z bar? Not enough
Yeah,
information.
yeah.
We don't know how deep it goes, so we can't just say. But if they had given you like some length here and said that this was, what's something reasonable? 250 millimeters, you could figure it out from there. But if it's symmetric, it would be just in the middle. So not enough info. All right. So this problem, for the first part, it says, find the moment of inertia about the y-axis. So I'm going to write them. Gosh, you guys are so needy. You're asking me for different things all at once.
I do recall you saying we could ask you to slide it if we needed.
Fine. So for I, y, I didn't solve this one the same way. So if this thing is symmetric about the y-axis, well, we'll just write it anyway. We have I, y prime plus a, that's not an a. I am confused. A times dx squared, right? And these are sums because it's looking at the composite figure. So it's each individual one. So I'm going to redraw this in a way that I don't know if you guys have seen yet. So if I draw my y-axis like this, okay, I'm flipping this thing over because I want you guys to kind of just imagine it moving. I'm going to say that I have this figure and I have this figure here. So this centroid of this one is right there. This one's right there. Do either of these have an x distance away from the y-axis? No. So do I need parallel axis theorem for this one? Right. So this here, this doesn't matter because the axis that we're looking for goes through the centroids of both of the problems. Therefore, we can just use the basic equations for it. So I'm going to call this figure 1. That's figure 2. So for I1, so IY1, so you guys know what is the equation for moment of inertia about, for a rectangle about its centroid? 1/12 BH cubed. Yeah. So we have, I'm going to write it up here, 1/12 BH, I need a piece of paper under this thing because there's like a rubber thing on the table. It's impossible to write on. So that's our I. So I always mention this in my sessions, but if I'm looking for I, y, for example, my base is a y value and my height is an x value. I just always make that clarification. So again, remember it's a moment. So the bigger component, that's going to be the perpendicular or the other distance, if that makes sense. So for figure number 1, oh, I didn't draw in distances. That's 150, that's 150. The depth is 50. This thing has a total length of 250. That's also 50. Okay. Figure 1, we have 1/12 times our base, which we said is going to be a y value. So for this one, that's 50, times our height, which is 300, and that's squared, right? Cubed, there we go. I wrote it and I said it like that on purpose because that's a very common mistake. I can't tell you how many times I've gotten a problem wrong only to look back on my calculator and realize that I had squared the value instead of cubed it. So be very careful. So then for figure 2, we have I, y2, 1 over 12. So our base is the y value, so that's 250. And then our height is 50. So my total IY is going to be the sum of both of those. And that gives me 1.15 times 10 to the 8 millimeters to the 4th. So that one was relatively quick. The next one is a bit more complicated.
I have a question. Can you explain why the A is 0?
The A is not 0. It's the dx value that's 0. So if I think that question will be better answered whenever we do the next part of this problem. Because then you'll see whenever it's not 0, and you'll understand why. But you see here that this is the centroid of this one, that's the centroid of that.
On the y-axis.
They're both on the y-axis. So the distance is 0.
Oh, because it's not.
Yeah.
Okay.
So the next part says, find y bar, which locates the centroidal x prime axis of the t-beam, and then find the moment of inertia about that x prime axis. So we have to find y bar first. So to do this, it's just a centroid problem. So y bar is the sum of y times a over the sum of a. So I have the segment. So we only have 2 segments. I have y tilde, I have a, then I have y tilde times a. And so just to redraw this figure, since I know I don't have much space on here, I have that and that. And I'm measuring my y tilde up from the x-axis, or my y bar upwards, because that's how they draw it on here. Notice that they draw this line right there. So that's the value they're looking for. And I just thought of a Star Wars reference. Anyway, this is figure 1, that's figure 2. No, that's okay. All right. So for segment 1, my y tilde is going to be this total height. Let me draw in the distances. That's 50. That's 250. That's good enough. So it's going to be 1/2 of 50 plus 250. So that gives me 275. The area, dang it, I needed that. That was 300. That value is 50. So the area of figure 1 is 300 times 50, which is 15,000. And then those multiplied together, that lovely large number. Then for figure 2, my y tilde is just going to be 1/2 of 250. So I have 125. The area is 50 times 250. So that's 12,500. Multiplying those, I get this other lovely large number. I need to add up a and y tilde a. So this is 5687500. This one is 27,500. So my y bar is 5687500 over 27,500. So that is 206.8 millimeters measured from the bottom. And this value does make sense. And I need, oh, that's perfect. Another piece of paper. So now, we need the parallel axis theorem for this problem. So for this one, we located our centroidal axis, which is right about here. So there's our centroid of this figure. We found that our y bar was 206 7 approximately. All right. So our equation for Ix, or Ix prime, so it's I about the centroidal x prime axis, is equal to the sum of I naught x, so that's the moment of inertia about the individual figures, plus the sum of A times dy squared. So drawing my table, I have my segment, I have my I naught, I have area, which I already have from before. I need to find these dy values. Then I have A times dy squared. All right. And there's not enough space. Okay. So for segment 1, segment 2, I'm just going to copy over the areas again. Okay. So for I naught for segment 1, so we know it's going to be 1 over 12 times the base times the height. But if I'm looking for it about this centroidal x prime axis, then that means my base is going to be the x value now. So notice that it flipped from before. So whenever I found, so going back up here, my IY, my base was 50, my height was 300. Now, my base is 300, my height is 50. So this gives me a large number, 3125 times 10 to the 3. For figure 2, it's the same sort of concept. So we have 1 over 12 times our base, which is now 50, times our height, which is 250 cubed. That gives me 1125 times 10 to the 5. We need to add up these values based on our equation, which is 6.82 times 10 to the 7. Now for our dy. So all that is, it's the distance between the centroid of the individual figures to the axis of interest. So for that problem, that axis of interest that we're looking for is the y bar that we found, okay? So what we plug in is, for figure 1, we know that our centroid, so I'm going back to this table here. We said our centroid was 275. So I have 275 minus my y bar for the entire figure, which is 207, and that's squared. That gives me 4624. Then for figure 2, my y, or my centroid for that one, is 125 minus my y bar for the figure, which is 207 squared. Notice that it doesn't matter which order you put them in, whether or not you get a negative value because it's squared. So this is 6724. So multiplying those values by the areas, we get more large numbers. 6.936 times 10 to the 7, and then 84.05 times 10 to the 6. We need to add these up according to our equation. So we get 15.341 times 10 to the 7. So my Ix prime is going to equal 6.82 times 10 to the 7 plus 15.341 times 10 to the 7. So Ix prime is 2.216 times 10 to the 8 millimeters to the 4th. Any questions about that problem?
So you went from finding the moment of inertia about y to
Those are actually two separate problems. So the Iy, that's independent of Ix. But in order to find the Ix prime, we had to find our y bar.
does the y bar change?
Yeah, so the y bar determined where that x prime axis was. So that's why we needed that. Are there any questions about this problem? This is a really good one. He basically, Dr. Alexakis basically told you guys that this one was going to be on your exam or something very similar to it.
What's the wording of the question? It's kind of confusing. Like, how would I know to use the y bar?
Well, this problem says determine y bar, which locates the centroidal axis x prime.
I didn't know if it was like straightforward or. Okay.
Yeah.
With like exclusions and holes, do we make the area negative or do we subtract that?
For which part?
So if we had a hole or exclusion for this type of problem, would we make the area negative
Yes.
and
So,
then just add it still?
very good. Yeah. So let's say, for example, you viewed this problem as a giant rectangle minus two like little rectangles. You would have to have the negative sign for your I naughts because you don't want, basically anywhere you end up having a summation, you want to make sure that those ones that don't actually exist get taken back out.
Okay.
So,
you want to make the overall thing negative because that would mess up the a y squared part?
yeah, so essentially the area, that would be negative, and then the I naught would also be negative. So hopefully this was helpful. The solutions will be posted hopefully tonight if I don't pass out before I get home. And if I don't fall asleep before I get home. But they will definitely be up by tomorrow.
What's the website name?
I will put the website back up here. Give me 1 second. Oh. So there is the website. So it's just my WordPress site, and it's statics with Alanna. So thank you guys.